So we are in the second half of the course, and where we are looking at continuous groups. And we began to look at the so-called classical groups. So in continuous groups I can write essentially matrix groups, sets of matrices with well-defined group properties. And then we are looking at classical groups, and then we characterize the classical groups by preservation of some metric. Of course, so if we go down the chain of preservation of some metric, then we get the SO n groups, the real groups that preserve Pythagorean metric of n dimensions. Or we can also get SO n comma m, where the Pythagorean metric has n number of plus signs and m number of minus signs. In the metric, and number of minus signs in the metric. So from this point of view, Lorentz group becomes SO31. And the rotation group is its subgroup. It is the first part, SO3, without the fourth axis. So it is just it properly contains SO3, which are rotations. We will see more about this. What we did next was to look at the generators. So these are matrices in terms of which we can generate the group by exponentiation. Where the exponential is now a matrix function. But it is defined exactly the same way by using the power series expansion. And we haven't seen all of it, so this is sort of being proved. Okay. We are gathering the evidence that this is possible to do. So we already saw that for SO3 we had the generators we saw that we have Lz equal to 0 minus 1 0 0 so 0 0 1 0 0 0 0 0 and similarly Lx Ly. Okay, you can work them out. And there was some philosophy about active rotations and so on. Okay. So this just defines the convention in which we did it, because you can get these signs opposite, but then you have to change signs everywhere, and they may correspond to what you may call passive counterclockwise, or you may call them active clockwise, etc. Now, the other thing we checked is that, so we checked that RZ theta was exponent of theta times Lz, and in general R n cap with an angle theta can be written as exponential of theta times n cap dot L, where L is short form notation for the three matrices Lx, Ly, Lz. We write it as if it is a vector, but physicists will understand this notation right away. Now, what we are doing next is that we are looking at SU2. Okay. So this all we worked out explicitly. We took a z-axis rotation, and then we made an expansion, and then checked that these are infinitesimal generator. We checked this, and we can see the reasonableness of this. We have not actually proved, but it can be proved. And we saw that need for Baker-Campbell-Hausdorff, so this can be checked. This is checked. And need for Baker-Campbell-Hausdorff identities in general. So we will see more about it a little bit later. What we do next is to look at the group SUO, and certainly most importantly these satisfy the algebra. So the antisymmetric algebra of the L matrices which is Li Lj equal to epsilon Ijk Lk, where Ijk equal to 1 to 3 instead of writing XYZ. Equivalently, we can introduce Ji Jj equal to I epsilon Ijk Jk, where J equal to I times, or Jk equal to I times the corresponding Lk. So we complexify the algebra, but then the J become Hermitian generators. So L are antisymmetric and J are Hermitian. So the fact that J is Hermitian will make its exponentiation a unitary metric. So it will give a unitary representation of SO3. We come to SU2. So as you remember, these are the matrices that preserves the metric on the complex vector space psi1 star psi2 psi1 psi2 psi2 star. This is the inner product on a two-dimensional complex vector space. So in any case, the condition on the unitary matrices was that U dagger U has to equal to 2 by 2 identity matrix. We want to characterize this matrix the same way we characterize the rotation matrix. So so we want infinitesimal version. So let U be equal to A, B, C, D. This is the most unimaginative but effective way of working it out. So you can imagine what is U dagger U going to be. Can you start writing down? Now this has to be set equal to 1 identity matrix. So it requires that, so we need and if we examine the off diagonal elements, then we see that A star B plus C star D equal to 0. The other element is just the complex conjugate of that. So there is, if this number is 0, then its complex conjugate will also be 0. So essentially we got that many conditions. In fact, for SUN, we can do this calculation. So we can do a counting here. We started with 4 complex numbers. Count independent parameters. There are 4 into 2 to begin with, but minus 3 real conditions. But so there are also, because the generic matrix is complex, so there appeared like there are 6 independent conditions because there are 3 conditions on complex numbers. But we have to restore it to the fact that it is unitary already reduces it by 1. Okay. So plus a 1. So it becomes 3 independent matrices. So the reasoning is that U dagger U is a Hermitian matrix. Right. So setting this equal to 1, in this case 2 by 2, basically gives 3 independent conditions, because 2 into 2 minus 1 n into n minus 1 by 2. So it gives 3 independent conditions, the 2 elements on the diagonal and 1 off diagonal, these 2 and this. but the conditions on the diagonal are automatically real. Okay, so this gives n into n minus 1 by 2 into 2 plus n real conditions. Okay, so suppose this is, if you take the case when this is general n by n, then because it is a Hermitian matrix, you need to consider only the upper diagonal, upper triangle and then the diagonal. The upper triangle has n into n minus 1 by 2 entries, because it starts with n minus 1, goes up to 1, right. So it has n into n, so this is upper diagonal entries, upper triangle, I am sorry. And because of complex numbers there is factor 2, but the diagonal does not give complex conditions. Because the matrix itself is Hermitian, the diagonal gives only real conditions. So this is the diagonal. Okay. So it gives this many conditions, which is equal to n into n minus so n square, so the 2 cancels, so n square minus 1 plus n sorry, n square minus n plus n. So it gives n square conditions on, in principle, 2 into n square entries of U. There is still something I have to count. We are starting with SU2, right? In fact, let us just think temporarily of SUN. What does SUN mean? I have some matrix U such that U dagger U has to be equal to n by n size identity. Forget all the other things that we did. Just look at this condition. How many conditions are there in this? And the conditions are that this is a Hermitian matrix, and that you can see on the right hand side also, it's identity matrix, which is a Hermitian matrix. If it is Hermitian matrix, its contents are this many off diagonal conditions, n into n minus 1 by 2 in the upper triangle times 2 because of complex numbers. So there is n into n minus 1 conditions from the upper triangle. On the diagonal, we have only n real conditions, because automatically, because of hermiticity, they don't have any imaginary parts. And so totally we have n square conditions here. This gives the this so far gives conditions on UN. So UN group characterized by n square parameters. Now we knew that the determinant of this such a U matrix can be a phase. Further note that U dagger U equal to det U dagger times det U. This is general theorem of matrix algebra. Determinant of product is product of determinants. So that makes it into det U mod square, because determinant of U dagger is same as the determinant of U star is the same as star of the det U. So this becomes det U squared. So if you set this equal to 1, so impose that this is equal to 1, then that means that det u is some phase. So it reduces the degrees of freedom in determinant u from 2 to 1. To det u equal to mod 1. Mod det u equal to 1, right? It reduces to a single complex number. So the 2 degrees of freedom in the determinant is reduced to 1. So there is a further reduction by 1 in the degrees of freedom in SUN. Free parameters, not degrees of freedom, but free parameters. So in the case of SU2, we expect 2 square minus 1 equal to 3 independent parameters. Free parameters. Okay. So I hope this logic is clear. The logic is only arguing the algebraically independent conditions that are being placed. Eventually the conditions wind up on the 2n square entries of the u itself, although the arguments all are made for the quadratic expression involving u dagger u. Okay. But that many algebraic conditions reduce the number of free parameters in the original matrix u, leaving n square elements in SUN and n square minus 1, because the determinant condition does not put 2 independent conditions but only 1, okay, on the complex determinant. Okay. So we have this many parameters. Now we can go back to SU2. So we can look at it like this. There is the matrix A, B, C, D, but we got the condition that A square plus C squared modular squares have to be 1, and similarly B square plus D square modular squares have to be 1. So we are immediately tempted to set A squared and mod A and mod C to be cos theta and sin theta, some cosine and sine. That is one way to think about it. This would be some other angle. Say if this is cosine phi 1 square, this is cosine phi 2 square, phi 1 square and cosine phi 2 square sine phi 2 square. So let me write it. The required constraints suggest that we can set mod A to be equal to, and now I am using somebody's parameterization for it, it looks useful, cos as sine phi and C mod C equal to cosine phi. We will see why this comes out useful. We will end up with Pauli matrices. Okay. So this is why we are writing like this. Now in principle I could have set B equal to some other angle psi, but the point is I also have to have this orthogonality condition between the A and the B. So that requires that this B has to be but orthogonal to A and C. So expect that B, so it is A star B. So B we can set equal to minus cosine phi and D equal to right sin phi. C equal to minus cosine phi and B equal to plus cosine phi. Okay, that much is okay. And then there is an overall phase which, so we can now introduce phases. So let me first rewrite this so that you feel a little reassured that we have here essentially A and A star and B and minus B star, and we further parameterize them by writing e raised to I theta times sin phi, then e raised to I gamma times cos phi, then minus e raised to minus I gamma times cos phi and e raised to minus I theta sin phi. So one way to think about it is that this much could be deduced directly from the mod square equal sum of mod squares equal to 1 conditions and the mutual orthogonality. That leads to this condition, because if you look at this matrix now, then it has automatically, if you mod A square plus mod B square, and those relations are satisfied. Now that this is still complex, because all we did was fix the moduli, so we got sin phi, cos phi and minus cos phi, but we are allowed to have some relative phases. So there are two independent phases you are allowed, again because of that complex orthogonality condition. You can't choose the phases completely arbitrarily. So we are allowed these two phases, theta and gamma. Okay. So totally we got three angles, phi, which characterize the mod square conditions, and then the two angles theta and gamma that follow from trying to ensure this. Okay. So this is the way in which one can write out the SU2 matrix, real. We are doing some rough work on the side. So we are just trying to, first guess is simply to put the modular, the sizes of them to be sines and cosines, and then we when we try to do the orthogonality thing, actually we come out with these conditions. Okay. So you can fool around with a bit and you will see that this is what it is. Yes. Yeah. So all I am saying is, if you look at these expressions, then you know that you have to put a relative minus sign when you get to, so you can put some phases. So you can now more systematically, you can start now with this. After having made a guess that you can put signs, you can put sine and cosine, right, because the mod square has to be 1. Now you also know that when you take cross product of the two, you should get 0. So they should be flipped as minus sine and plus cosine or vice versa. It's just guesswork. And then you say that I am still left with a phase which is independent as far as A and C is concerned. A and C can have independent phase, but because of the product, B and A are not allowed to have independent phase. So that fixes their phases to be opposite. This and this and this and this, plus I gamma and minus. So it's a guesswork as to what the form should be. Then we get this, and we can see that it satisfies the required conditions, because mod A square plus mod C square. We can quickly see now, compare that. So this originally was A, B, C, D, and with mod A square plus mod C square equal to 1, which we can see is true, right? A and C, mod A square plus mod C square. Mod B square plus mod D square is equal to 1, and then A star times B is e raised to minus I theta e raised to plus I gamma sin phi cos phi, and then plus C star D, but C star is still equal to minus sin e raised to plus I gamma and times cos phi, and times D is e raised to minus I theta times sin phi. So the phases came out now equal, e raised to minus I theta plus I gamma, but there is a relative minus sign, so this will cancel and will give 0. So this parameterization parameterizes the SU2 matrices.